We discussed translation in the previous class. In this class, we'll discuss momentum as a generator of translation. We have the fundamental commutation relations between the position operators and the k operators. Okay, this is something that we did in the previous class. We found these commutation relations. Okay. Now, so far the k operator is defined in terms of the infinitesimal translation operator. So this is where k appears. We write the infinitesimal translation operator as the identity operator minus I k vector dot dx vector prime. This is where we introduced the k operator. Right. The next question is, does this k operator here have any physical significance? Can we attach any physical significance to this k operator? Now we'll take a hint from J. Schwinger. He said, for fundamental properties, we will borrow only names from classical physics. Okay, so we'll borrow some names from classical physics. So we'll look at classical physics and see if we can associate k vector with something, all right, with some name in classical physics. Right. In the present case, we would like to borrow from classical mechanics the notion that momentum is the generator of an infinitesimal translation. Right. So if you have studied classical mechanics, you already have heard this. Momentum, linear momentum, is actually the generator of an infinitesimal translation. Okay. So this means that here we are talking about translations, and we said that translations are written, the infinitesimal translation operators are written like this: I k vector dot dx vector prime. All right. So taking a hint from classical mechanics, will suggest that this k vector is somehow associated with momentum. Okay. Let's first have a quick look at classical mechanics. In classical mechanics, an infinitesimal translation can be regarded as a canonical transformation. You might be familiar with the canonical transformations. A canonical transformation is a transformation in which you go from an old set of coordinates and momenta to a new set of coordinates and momenta. If you are talking about a single particle, these coordinates can be represented as x vector and the momenta as p vector. So this has three components, and also momentum has three components, right? So this is the old coordinates and momenta, and the new coordinates and momenta can be represented as capital X vector and capital P vector. All right. Then an infinitesimal transformation does this, right? The new coordinates x vector is equal to the old coordinates x vector plus dx vector. Okay, and the new momentum given by p vector is equal to the old momentum. So the momentum does not change, but the coordinates change in this manner. Right? We call this as coordinates because we have got three components. So if you are talking about Cartesian coordinates, this x vector will have three components: x, y, and z. So these are the coordinates here. Right? So we are just denoting this. We are just representing all these three coordinates into one object called x vector. That's all. Right? It's the same thing. Now, such a transformation, this is an infinitesimal translation. Right? Now, such an infinitesimal translation can be obtained from a generating function of this form: f of q x vector comma capital P vector is equal to x vector dot capital P vector plus P vector dot dx vector. Okay. Now, this generating function is a mixed function of the old coordinates and the new momenta. The old coordinates and the new momenta. Okay. Now you can find the transformation equations from one set to other by these relations. Right. So once we are given a generating function like this, f is equal to f of x vector comma capital P vector, then we can write. So let me just write it like this: f of x vector comma capital P vector. Let me write it in the component form. So this would be, let's say, xj capital Pj. There's a sum over j implied, plus this is small pj dxj. Right? So this is the sum over j is implied here. We are following Einstein's summation convention. Okay. Now in this case, you can find you have these relations. If the generating function is of this form, we have the relations pi is equal to the partial derivative of f with respect to xi. All right. And similarly, we see that capital Qi, in this case, this is written as capital Xi, the new coordinates Okay, this is equal to the partial derivative of this generating function with respect to pi. Right? So you can go back and check your textbook on classical mechanics. You can look at Goldstein and you'll see these relations. All right. Now you try this. Use take this generating function, find these derivatives, and you'll see that the new coordinates are equal to x vector plus dx vector, and the old coordinates are equal to, and the new momenta are equal to the old momenta itself. Okay, so this is an infinitesimal translation, but this can be seen as a canonical transformation generated by this generating function. Okay, and this thing, all right, we used to call this as the whatever appears here, we used to call as the generator of a particular transformation. This was called as a generator of a particular transformation. Here we are talking about translation, and in that case, the generator was the linear momentum. Okay, so we said in classical mechanics that linear momentum is the generator of infinitesimal translations. Infinitesimal translations. All right. Even though the full generating function is f, whatever appears here we used to call as the generator of infinitesimal transformations. In this case, the transformation we are talking about is a translation in space. All right. So I leave this as an exercise for you to show that if we start with this generating function, the canonical transformation generated by this generating function is exactly an infinitesimal translation. Okay. This equation of this generating function, it is strikingly similar to the infinitesimal translation operator in quantum mechanics. All right. So in quantum mechanics, we had the infinitesimal translation operator, the unitary operator corresponding to infinitesimal translations. We had written it as j of dx vector prime is equal to the identity operator minus I k vector dot dx vector prime. Right. Now, what's the similarity between this and this? The similarity is that in classical mechanics, if this is the generating function, right, if this is this particular generating function x vector dot capital P vector, okay, this is actually a generator of an identity transformation, right? This is generator of identity transformation, which means that if this is the generating function, then we will have x vector is equal to, or capital X vector is equal to small x vector, and capital P vector is equal to small p vector. All right. So this generator or this generating function, okay, this generating function corresponds to an identity transformation, all right? So here also we have this identity, here also we have got this identity, all right? So this generates an identity transformation, and here in the quantum mechanical case, this part corresponds to an identity transformation, all right? And the other parts are also similar. Here we have got something dot dx vector, here we have got k vector dot dx vector, right? K vector dot dx vector, there's an I that appears in quantum mechanics also, all right? So this suggests that we can relate this k vector, perhaps we can relate this k vector with the momentum. Maybe we can call this the momentum, right? So we are therefore led to speculate that the operator k vector is in some sense related, at least, to the momentum operator in quantum mechanics. Right? We haven't defined the momentum operator yet, but this seems to be a good way to define the momentum operator, because in classical mechanics we have got the generator of infinitesimal translations as momentum. We wrote down a unitary operator for uh, infinitesimal translations in quantum mechanics. All right, and in that we have got an operator sitting here, a Hermitian operator, right? And we know that observables are represented by Hermitian operators. So momentum is an observable, so there should be a Hermitian operator corresponding to that. Okay. Now, since linear momentum is a generator of translations in in classical mechanics, whatever generates a translation in quantum mechanics can be called or can be related to the momentum operator. All right, I'll repeat. If the linear momentum, right, if the linear momentum is the generator of translations, of infinitesimal translations in classical mechanics, whatever generates, right, whatever generates an infinitesimal translation in quantum mechanics can be associated with the momentum. Okay. So the next question is, can the k operator in here, I minus or 1 minus I k vector dot dx vector prime, can the K operator here be identified with the momentum operator itself? Can we call this the momentum operator in quantum mechanics? Right? But this doesn't work because the dimension is all wrong. Okay, the K operator has the dimension of 1 by length. This is, you can think of this as a transformation matrix if you are working in a particular basis, right? And we need these quantities to be dimensionless because this would act on a vector and change it into another vector, right? So these things have to be dimensionless, which means that this has the dimensions of length, which means that K vector should have the dimensions of 1 by length in such a way that the entire thing is dimensionless, right? Because here we have the identity operator. So if you are subtracting something from the identity operator, it has to be something that's dimensionless, right? So by construction, this K vector here has to be dimensionless, which means that it should have dimensions 1 over length in such a way that this K vector dot dx vector prime becomes dimensionless, right? So what we can do is that we cannot identify this with the momentum, okay? But we can still introduce a momentum operator. This has the dimensions of momentum, obviously, because this is the momentum, okay, and divide it by a quantity, right, some constant. Suppose there's a universal constant with the dimensions momentum multiplied by length, momentum multiplied by length, right? So if you have some universal constant with momentum multiplied by length, we could divide the momentum operator by this universal constant, and then we would get K vector. So we can write K vector equal to P vector divided by momentum multiplied by length, or a universal constant with the dimension momentum multiplied by length, right? Now such momentum multiplied by length, this is also called an action, but this is also called an action, right? So but if it is moment, you could think about it as momentum multiplied by length, px, or energy multiplied by time. All these have the same dimensions, okay? Momentum multiplied by distance or length, energy multiplied by time, all these have the same dimensions, okay? And this is called an action. Such a quantity is called an action, all right? So we could still relate K vector to P vector by dividing P vector by a universal constant with the dimension of action, okay? From the fundamental postulates of quantum mechanics, there is no way to determine the actual numerical value of the universal constant. Right? This constant is needed here because historically, classical physics was developed before quantum mechanics using units convenient for describing macroscopic quantities. Okay, for example, they may have to talk about the circumference of the Earth, all right, the mass of 1 centimeter cube of water, the duration of a mean solar day, and so forth. All right. So that the units that we have now, this meters, seconds, centimeters, kilograms, etc., right, these were invented out of practical necessities, out of practical needs. All right. So we did not take a hint from nature to construct a unit system. We just constructed the unit system according to our convenience. Right? We fixed certain length to be 1 meter, etc. All right. But actually, if we take hints from nature, for example, right, in special theory of relativity, we know that c is given as the speed of light is 3 into 10 raised to 8 meter per second. Right? These are in the units that we invented. Right? Meters are the units that we invented. Seconds are the units that we invented. All right? That's the reason why this looks rather a weird number. But if we took a hint from nature, right, if we knew relativity all along, we could have set c equal to 1 in the beginning because it's a universal constant, and then define the units according to this thing, right, based on this definition. Right? In the same way, if there's a fundamental constant in quantum mechanics, right, if we knew quantum mechanics from the beginning, we could set this fundamental constant to be 1 and then define all other units accordingly. Right? So there is such a unit system. It's called the natural system of units. Right? That's called the natural system of units. Right? So in natural system of units, all these important constants, the universal constants, are set to 1. Right? And then everything else is built up from there. But we are not working with natural system of units. Right? This is the reason why we now have to introduce this constant, right, with the dimension of action. Right? So from the fundamental postulates of quantum mechanics, there's no way to determine the actual numerical value of the universal constant. All right? Now, if microscopic physics had been formulated before macroscopic physics, the physicists would have almost certainly chosen the basic units in such a way that the universal constant would be unity. So we have this thing, we said that k vector is equal to p vector divided by a constant with the dimensions of action, right? If there is such a universal constant, right, if there is such an important universal constant, we could start by fixing this, the value of this universal constant equal to 1, and then construct all other units based on this definition, right? But unfortunately, this is not how things worked out historically. So that's the reason why we have to introduce a universal constant which has a value other than 1, right? And this number has to be found out through some sort of experiments, right? This number or this universal constant has to be found out through some sort of experiments, okay? So we are looking for a universal constant with the dimensions of action, right? You might have already guessed this universal constant. Of course, it's nothing other than h bar, right? H bar is a universal constant with the dimensions of action, so it should work here, all right? So we can say that our k operator is equal to p operator divided by h bar. We can make this identification. All right. So what we have done here is that we have defined the momentum operator in terms of translation. We have just defined the momentum operator in terms of translation. All right. Now this h bar is the same h bar that appears in de Broglie relation. You might have heard of this relation. Lambda is equal to h by p. This was called the de Broglie wavelength. Okay. Now we can write this as this is equal to h bar multiplied by 2 pi divided by p, right? Or we can write 2 pi divided by lambda is equal to p divided by h bar. Okay, so we have a relation here. Momentum divided by h bar is equal to 2 pi divided by lambda. Now, corresponding to the momentum, we have got the momentum operator. We have defined the momentum operator. H bar is a constant, right? This means that the operator appearing here is the operator corresponding to this quantity 2 pi divided by lambda. Now this 2 pi divided by lambda is called the wave number. Okay, so this k vector that we introduced in this infinitesimal translation operator, all right, k vector dot dx vector prime, this k vector that's appearing here is understood to be the operator corresponding to the wave number. All right. So the k operator is the quantum mechanical operator that corresponds to the wave number, that is 2 pi times the reciprocal wavelength, usually denoted by a small k or a small k vector, if you include also direction. Okay. So this is wave number. We can define a wave vector also. All right. So we can say that this k vector operator that appears in this infinitesimal translation is the operator corresponding to the wave number. Okay. So this was our translation operator that we started with. J of dx vector prime is equal to the identity operator minus I k vector dot dx vector prime. Okay. Now by looking at translations in classical mechanics, we said that whatever appears here can be associated with the momentum. Right? We can define a momentum based on this translation. Right? The only problem is that this k vector cannot be called the momentum because it does not have the right units. This should have the units 1 divided by L, whereas momentum should have the units of momentum. Right? So we define a momentum in such a way that k vector is equal to momentum divided by a universal constant, right? P vector divided by h bar, in such a way that k vector has units 1 divided by L. H bar is a universal constant with dimensions of action. Right? Once we made this identification, we can write j of dx vector prime is equal to 1 minus I p vector dot dx vector prime divided by h bar, where p vector is the momentum operator. Okay, so we can call this momentum operator now as the generator of translations, All right. Now the commutation relations, we also had the commutation relations xi with ki is equal to I delta ij. So xi with kj is equal to I delta ij. Okay. Now since kj is equal to p by h bar, right, so this is equal to xi with pj divided by h bar is equal to I delta ij. Right? Now if you look at this h bar can be multiplied throughout. It appears in every term. So this becomes xi with pj is equal to I h bar delta ij. Right? We can just check this. All right? If you expand this commutator, you will see that there's an h bar appearing in the denominator of every term on the left side. So you multiply throughout by h bar and you get the commutational relations xi with pj is equal to I h bar delta ij. Now these commutation relations imply that x and px are incompatible observables. These are incompatible observables. Okay. It is therefore impossible to find simultaneous eigenkets of x and px. Okay. Which is another way of saying that there is no state with a definite value for x and p simultaneously. Right? You could think of a position eigenstate which has a definite value for position, but that state cannot be an eigenstate of momentum, or it cannot have a definite value for momentum. Okay, so there are no quantum mechanical states with a definite value of position and momentum at the same time. In other words, there are no electrons with a definite value of position and momentum. Right? There are no electrons which have simultaneously a definite value for position and momentum. Now, this indeed is the reason for the Heisenberg's uncertainty relation, which says that you cannot determine the position and the momentum of an electron simultaneously with complete accuracy. Okay. That leads us directly to the general uncertainty relation of Heisenberg. Right? Now we see that the commutator of xi with pj is I h bar delta ij. Right? We see that these are incompatible observables, and we had found an uncertainty relation for any pair of incompatible observables. Okay, that was our generalized uncertainty relation. Right? So it was found in terms of the commutator. So you use the generalized uncertainty relation and just substitute x and p instead of a and b, and you get this Heisenberg uncertainty relation. Okay, you get this Heisenberg uncertainty relation. Right? So I leave it as an exercise for you to substitute this thing in the generalized uncertainty relation and find the Heisenberg uncertainty relation. All right. So far we talked about infinitesimal translations. We can now talk about a finite translation. A finite translation is a spatial displacement by a finite amount. So instead of an infinitesimal translation, now we are talking about a finite translation. Right? Now the idea is that a finite translation can be obtained by successively compounding infinitesimal translations. We already found an operator for an infinitesimal translation, a unitary operator corresponding to infinitesimal translations. So we can build up a finite translation out of a large number of infinitesimal translations. Right? So a finite translation in the x direction by an amount delta x prime is defined like this. Okay, this is the amount by which you are translating. This is the direction in which you are translating. The corresponding operator acting on x vector prime gives you obviously x vector prime plus delta x vector hat. Right? So this is the definition of a finite translation in the x direction by an amount delta x prime. We are talking about a translation by a finite amount delta x prime. All right. The idea that we are going to use here is to divide this delta x prime into n equal segments. Right? N equal segments. Capital N equal segments. So each segment, right? Each section will have length delta x prime divided by n. Right? Now, in the limit n tends to infinity, this is nothing but dx prime. Right? So the idea is that we can think of this finite interval or finite length delta x prime as constituting of a large number of infinitesimal segments of equal lengths. Right? So we can find the entire translation by first taking the small translation here and then the other translation and then the next translations. So the idea is that we'll make n capital N translations, each of length delta x prime divided by n. Right? Now if I talk about the limit n tends to infinity, then we are talking about infinitesimal segments, right? Sections of infinitesimal length, and there we can use the formula for infinitesimal translations. Right? So this is how we construct the finite translation operator. J of delta x prime in x direction is limit n tends to infinity. Right? And what we have inside the bracket is the operator for an infinitesimal translation. Right? 1 minus ipx delta x prime divided by nh bar. This delta x prime divided by n in the limit n tends to infinity is an infinitesimal interval. Right? So what's inside the bracket is actually one infinitesimal translation. So if you look at our operator for infinitesimal translation, it was this 1 minus I p vector dot dx vector prime divided by h bar. Alright. If you are talking only about one direction or the x direction, this becomes 1 minus ipx dx prime divided by h bar. Alright. So that's exactly what we have here. Instead of this dx prime, I have delta x prime divided by capital N. So here, and then you do this capital N number of times. So we have divided up this into equal segments. So you just do this a capital N number of times, where N is the number of different segments. All right. So if you do this in a capital N number of times, then you'll get a translation corresponding to delta x prime. Okay, that's why we write j of delta x prime is limit n tends to infinity 1 minus ipx delta x prime divided by nh bar whole raised to n. Okay. Now this thing, right? If you apply the limit, we identify this with the function exponential. Right? This is exponential minus ipx delta x prime divided by h bar. I think this function is called the exponential function or exp function. I don't know. The definition for the exp function is this: exp of x is equal to 1 plus x square by 2 factorial plus x cube by 3 factorial, etc. Right? This is the definition for this function. You can take this as the definition for this function. All right. So we need to take this expression, apply the limit n tends to infinity, and it will reduce to this expression. Right? It's easy to show this. So what we need to show is actually, if you have something like 1 plus x divided by n whole raised to n, okay, in the limit n tends to infinity. Okay, we need to show that this is actually equal to e raised to x. Sorry, not e raised to x. It's one way of writing it is e raised to x, but it's better to write it as exp of x or exponential x. Right? Now it's easy to show this. We just use the binomial expansion. There are different ways to do this. Right? We can do this by making a binomial expansion. So this is actually, we know the binomial expansion. 1 plus x raised to n is 1 plus nx plus n into n minus 1 by 2 factorial x square plus etc. Okay, so we apply that here. This is equal to 1 plus n 1 plus nx. So n multiplied by x divided by n, that is simply x plus n into n minus 1 divided by 2 factorial, and I have here x square divided by n square, right? Because the square of this thing, it's x square by n square plus etc. It goes like that, right? But it's easy to see the trend here. So if we look at this, this can be written as 1 plus x plus, this can be written as n square minus n, right? N square minus n divided by 2 factorial and then n square x square, right? You can check the third term also. Let me make some space here. Now this can be written as 1 plus x plus, right? You see there's an n square here. We can divide this n square out. So there are two terms here. First term is n square divided by n square is gone. So 1 by 2 factorial. Okay, 1 divided by 2 factorial x square. There's one more term here, minus 1 by n. So minus n divided by n square. That is 1 divided by n x square. All right. Now there are, you can find the other terms also. From the third term, you will see that there's a term x cube by 3 factorial and then another term involving 1 by n or 1 by n square. Right. Anyway, now you apply the limit n tends to infinity. This term will go to 0. When you apply the limit n tends to infinity, this term will go to 0, and there will be terms with n in the denominator. All those terms will go to 0. You can check that, right? And you will be left with, after applying the limit, you will be left with 1 plus x square divided by 2 factorial plus x cube divided by 3 factorial plus etc. Which is nothing but the definition for the exp function, exp function. Right? So that's why we write this j of delta x prime, j of delta x prime as limit n tends to infinity 1 minus ipx delta x prime divided by nh bar whole raised to n, and you make a binomial expansion and apply the limits. This reduces to exponential or exp minus ipx delta x prime divided by h bar. Okay, I just told you how to check this. So please try it also, right? See if it actually works. Okay. So we have got now an operator, a unitary operator for a finite translation, unitary operator for a finite translation. Okay. Now I leave it to you to check whether this is unitary. Actually show that this is unitary. Show that this operator that we have constructed here is actually unitary. It's easy to check this. All right. Okay. Also, I leave it as an exercise to prove that limit n tends to infinity 1 plus x divided by n whole raised to n. Okay. It can be written as exponential of x, right, or exp of x. Okay. There are different ways of doing this. The trick that we used is to make a binomial expansion and then take n tends to infinity. So all the terms that are left with an n in the denominator will vanish. That's the idea. Okay. Now I have already sketched how to do this. All right. I ask you to do it correctly. Okay. Now, a fundamental property of translations is that successive translations in different directions, say in x and y directions, commute. Okay, so we can think about different translations, one along x direction, the other one along the y direction. We could think of this in opposite orders, right, in different orders. First, we can think of a translation in the x direction and then along the y direction, right? And then we can think about a y translation in the y direction first and then along the x direction, right? Now, it doesn't matter in which order we do this, we'll end up at the same point. Right? This means that the translations, successive translations in different directions commute. Right? This can be seen from the. So this is what we do. We start at point A. Right? First, I make a translation along the x direction by a length delta x prime, then along the y direction by a length delta y prime. Where do we reach? Let's say that we reach the point B. Right? Now, in the second case, you start with A, start at the point A, and first you make a translation along the y direction by an amount delta y prime, that will take you to D, right? And then you make a translation along x direction by an amount delta x. That will take you again to the point B. So it doesn't matter which of these translations you do first. You could translate along y first, or you could translate along x first, right? In both cases, we reach the same point. So in shifting from A to B, it does not matter whether we go via C, right? It doesn't matter whether we first go to C and then go to B, or we go first to D and then go to B, all right? So mathematically, we can write this statement like this, right? In this case, first I apply a finite translation by an amount delta x prime in the x direction, right? And then I follow it by a finite translation along the y direction. Right? In the result, the end result is that this is a translation of delta x in the x direction plus delta y prime in the y direction. Right? So if you look at this vector, delta x x prime, so delta x prime x vector hat plus delta y prime y vector hat, this is simply this vector. Right? It's the vector from A to B. Right? This is a property that we have initially seen, right, when we have two successive translations. The we should be able to write it as one translation. We should be able to write it as one translation, right? We have seen this property, right? The second case, we see that first we apply translation by an amount delta y prime along the y direction, and then translation by delta x prime along the x direction, right? And again, I am reaching the point B. So this can be written as a translation from A to B. This also can be written as a translation from A to B. Right? That's what we have written here. It's a translation along this vector A to B. What is this vector? This is delta x prime x hat plus delta y prime y hat. Right? So both these operations give us exactly the same result. Right? So in this case, first I do delta x prime and then delta y prime. All right, and that gives me a translation along this direction. Right. Second, I first in the second case, I first do delta y prime and then I do delta x prime. Again, I get the same translation. Right, the translation corresponding to the vector from A to B. That's this vector, which means that we can simply equate this. These two are equal. These two have to be equal. All right. Now, this may seem trivial at first sight, but it's not actually trivial. Right? For example, we'll see that in the case of rotations, rotations along different directions or different axes do not commute. This is something that we have seen in classical mechanics also. Right? We have seen that finite rotations do not commute. The order in which you make the rotations actually matters. Right? All right. So let's find the commutator of these operators. We said that they commute. Right? Let's actually write down the expression for this commutator. So we substitute for the translation operator along the y direction and the translation operator, the finite translation operator along the x direction. We expand them. Okay? This is the expansion of this term. In the first bracket is the expansion of x minus I py delta y prime divided by h bar. Similarly, the corresponding translation operator, the translation operator corresponding to finite translation along x direction is expanded in this bracket. Right? Now we find the commutator, and the commutator is written as, for example, if you have a commutator like this, a plus b with c plus d, we can simply write this as a comma c plus a comma d, okay, plus b c plus b d. All right, I leave it as an exercise for you to prove. Okay. You just have to do a plus b multiplied by c plus d minus c plus d multiplied by a plus b. All right, and see if you can write it in this form. All right. So once we do that, we can write down the expression of this commutator. The identity operator commutes with everything, so we don't worry about that, right? So we look at the second term, it commutes with this term, right? So the only thing that we need to write down is the commutator of this term with this term, right? There are also higher order terms, but uh, let's look at the terms up to the second order in this translations. All right, let's look at the commutators up to second orders in this second order in these translations. All right, so we see that up to second order, this is written as this delta y prime delta x prime just get multiplied. All right, there's also this rule: if you have a constant, okay, C A with B, this is simply C multiplied by commutator of A with B. So the constants can be pulled out of the commutator bracket. Right? This also you can prove. The constants can be pulled out of the commutator bracket. So there's a minus I here, they multiply it to give minus 1. Okay. This delta y prime, delta x prime are distances, they come outside. Okay. There's an h bar here and an h bar here. So we have got an h bar square. What we are left with is the commutator of py with px. Okay. Now we said that the translation operators actually commute. That means that this is 0. In other words, the commutator of py with px is equal to 0. Right? So based on the fact that the translation operators are commuting, the translations along different directions commute, we have identified the commutation relations for different components of momentum, for the different components of momentum. All right. Now remember, we are defining momentum entirely in terms of properties of translation. Right. We defined momentum as whatever generates a translation in space. Okay. Now the commutation relations among the components of momentum is derived from the fact that translations among different directions have to commute. Okay. Right. So this requirement that these translations commute leads us to a commutator of px with py equal to 0, or generally the commutator of pi with pj equal to 0. Different components of the momentum operator commute among themselves. You already know that this is not true for the case of spin. We also have a spin operator. Its components can be written as Sx, Sy, Sz, but the different components of the spin operator do not commute among themselves. Right? So this is an important statement. It's not at all trivial. It's not at all trivial. This means that we will be able to specify the x component of momentum and y component of momentum simultaneously. All right. Whereas we will not be able to specify the x component of spin and y component of spin simultaneously. All right. So this commutation relation is a direct consequence of the fact that translations in different directions actually commute. Now, whenever the generators of transformations commute, the corresponding group is said to be abelian. So we are talking about translations, and if you are thinking of a group of translations, right, that will be an abelian group. This translations will form a group, and that is called an abelian group. All right. So whenever the generators of transformations commute, the corresponding group is said to be an abelian group. The translation group in 3 dimensions is abelian, right? Whereas the rotation group in 3 dimensions is not abelian, it's a non-abelian group, but these things we'll be seeing later on. Okay? Now, these commutation relations imply that Px, Py, and Pz are mutually compatible observables because they commute among themselves. Right? Now, we can therefore think of a simultaneous eigenket of Px, Py, and Pz. Right? Whereas we cannot specify Sx and Sy simultaneously, we can specify Px, Py, and Pz simultaneously, and the corresponding eigenket can be labeled with the eigenvalues. Okay, so we'll give this ket p vector prime is equal to ket px prime, py prime, and pz prime. So we are labeling the momentum eigenstate, the eigenstate of the momentum operator, by giving the eigenvalues of all 3 components. Right, so these are the eigenvalue equations. Px operator acting on ket p vector prime gives you the eigenvalue px prime multiplied by ket p vector prime. Similarly for py and pz. Right? Now this is exactly analogous to what we discussed in the case of positions. In the case of positions also, we defined these simultaneous eigenkets of x, y, and z. Okay. Now let's look at the effect of the infinitesimal translation operator on a momentum eigenket. Okay, so this is infinitesimal translation operator acting on a momentum eigenket. I put in the infinitesimal translation operator here. I have got the momentum operator sitting here, right? But since this is an eigenvalue, right? So there's this rule: if you have a function of an operator acting on an eigenket of this operator, then this is simply the function of the eigenvalue multiplied by the same ket. Right? This can be easily proven. This can be easily proved. Right? A function of an operator acting on an eigenket of this operator is equal to a function of that eigenvalue multiplied by the ket. Right? So here we have this 1 minus ip vector dot dx vector prime by h bar acting on ket p vector prime. Right? But this acting on this, we know that this ket p vector prime is an eigenket of this operator. Right? So we can simply replace this by the eigenvalue. Right? So we see that this is what happens on a momentum eigenket, right? Under an infinitesimal translation. We see that the momentum eigenket remains the same even though it suffers a slight phase change. Right? We see that it's the same. The momentum eigenket remains the same. This you can think of as a phase change because if you take the modulus square, this will be 1. But if you take the modulus square of this number, it will be 1. But of course, you have to do this by retaining the first order quantities. Right? You could also check this with finite translations. You can check this with finite translations, and that also it's clearly seen. You will see that you will get the same momentum eigenket multiplied by e raised to I something. Right? You'll get e raised to I p prime, let's say delta x prime divided by h bar. This is a pure phase factor. Right? So this means that the momentum eigenket remains the same even though it suffers a slight phase change. So giving it a phase factor does not change it physically. Right? We have discussed this thing. Right? This does not change the probabilities. It does not change the normalization. So in effect, it does not do anything to the state. Right? There is no physical change if you are simply multiplying with the phase factor. Right? So in effect, we see that the momentum eigenket remains the same. So unlike x vector, ket x vector prime, ket p vector prime is an eigenket of the infinitesimal translation operator. Now this is understandable because p vector actually commutes with the translation operator, right? The momentum operator commutes with the infinitesimal translation operator, as we can easily see, because this is a function. This translation operator is actually a function of the momentum operators, and the components of momentum operators commute among themselves. Okay? So this commutator is also 0, which means that an eigenket of p operator is also an eigenket of this thing, that infinitesimal translation operators, because commuting observables have common eigenkets, as we have proved before. Notice, however, that the eigenvalue of the translation operator is complex. The eigenvalue is actually complex. You see this? You see that this is complex, right? Now, this is also understandable because we do not expect a real eigenvalue. We expect a real eigenvalue for a Hermitian operator, but this is not a Hermitian operator. This is not an observable, right? It does not represent an observable. The translation operator does not represent an observable. It's not a Hermitian operator, right? So its eigenvalues can be complex. right? So J of dx vector prime, though unitary, is not Hermitian. So it's an operator which is unitary but not Hermitian, right? We started with the infinitesimal translation operator. We said that it should have the form the identity operator minus I k vector dot dx vector prime. Right? We saw that k vector has to be Hermitian, so that this is a unitary operator, etc. Right? Now, by looking at classical mechanics, we say that we are tempted to define this k vector as the momentum operator. Right? We are tempted to call this as the momentum operator because in classical mechanics, the generator of translations is momentum. We are tempted to call this the momentum operator, but there's a small catch. It does not have the right units. But this is easily fixed. This is easily fixed. We say that k vector is actually the momentum divided by universal constant with dimensions of action. Right? With this, we have the infinitesimal translation operator as I p vector dot dx prime divided by h bar. Right? So we have basically defined the momentum, quantum mechanical momentum, by demanding that momentum has to be the generator of translations. Right? So whatever appears here, we should identify as the momentum. This was the basic idea. Okay? Whatever appears here should be associated with the momentum. All right. Then we found that any finite translation can be constructed out of infinitesimal translations. Right? And we saw that the finite translation, corresponding to finite translation, we can write exponential, the operator corresponding unitary operator is exponential minus I p vector dot delta x prime, the delta x prime, divided by h bar if you are talking only about the translation along the x direction. Okay, so if you are talking about the translation in x direction, we'll have a px here. Right? So in general, the translation along any direction can be written as exponential minus I p vector dot delta x vector prime divided by h bar. Then we looked at some of the properties. We saw that based on the fact that translations commute, different translations or translations along different directions commute, we found the commutation relations between the components of the momentum operators, and we saw that they commute. This means that we can define common eigenstates for operators px, py, and pz, and we said that we'll denote this as ket p vector prime. This common eigenstates will be, or common eigenkets will be denoted as ket p vector prime. Right? We also saw that this ket p vector prime is also an eigenket of this translation operator, but with complex eigenvalues because this is not a Hermitian operator. These are the things that we have discussed in this section. Okay. So with that, I'll conclude. Thank you.